All right, welcome to the 5.2 video for Math 31, which is all about horizontal asymptotes. Pretty logically, I think. We talked about vertical asymptotes in 5.1, so in this section we talk about horizontal asymptotes. And you learned a little bit about them in Math 30-1. We taught you a bit of a weird technique where we consider the degree of the numerator and the denominator. We're going to use a much more kind of, maybe not official is the right word, but definitely algebraical technique for finding it, which is the limit as x goes to infinity or negative infinity. And I think, again, if we think about horizontal asymptotes, it is about the behavior as x approaches positive infinity and the behavior as x approaches negative infinity. Now, it's very important that not all graphs have horizontal asymptotes. If we draw the graph of y equals x squared, just for example, that's the parabola that opens up, this function does not approach a value as x becomes large. In fact, if we took the limit as x approaches, and it's actually positive or negative infinity of x squared, we get positive infinity. And that's all about the end behavior of this graph, which is the terminology we used in 30-1. There are plenty of different ways of approaching a horizontal asymptote. I'm just going to show you, I think there's actually 6 in the notes here. Keep in mind that we would identify a horizontal asymptote at some value L, and I'm just going to put it about the same place on all my graphs here. Certainly the most typical is this, where the function is below or less than the horizontal asymptote and then approaches it. The graph, it is about the end behavior. So we could have a function that rises above the horizontal asymptote, but then approaches it from the above or from greater than that L value. Both of those have a horizontal asymptote. Some of the stranger ones, though, are graphs that seem to kind of oscillate above and below and get closer and closer and closer, and then eventually have that asymptotic behavior. And similar to the last one, we can have that asymptote on the left-hand side and not on the right. Right, lots of different just examples of the asymptotic behavior. And I can't stress enough that when we talk about where that asymptote is, it's about where the function is approaching the value L, but not actually being equal to it. So when we talk about those horizontal asymptotes, very important to look carefully at that graph. All right, a couple other ways, and certainly these aren't really different than the ones before. One that students tend to struggle with is the idea that we can have a different asymptote on the left-hand side than we do on the right-hand side. And this would be maybe just as a quick example, the graph of y equals the arctan of x. That has a very, very strange shape to it. The other example I have in the notes is really, I think, overkill or maybe overlap, I suppose. We can have that weird behavior, and it's almost like nothing matters. And when I'm boxing here, what we want to think about when we talk about the asymptote is the far left and the far right side of that number line. That's where our horizontal asymptote behavior maybe shines through, if we want to say it that way. So it's very, very important we consider that. That being said, there are a couple kind of classic or maybe kind of constant limits we run into. Maybe constant limits, a bad choice of words, but these are some regular infinite limits. So above we have the limit as x approaches infinity of 1 over r, x to the power of r. But really importantly, r has to be a positive rational number. So if I had y equals 1 over x to the power of 3/5 as an example, this limit, or the limit of this as x approaches infinity, would be 0. And then the other case is that it's true on either end. And what's really important about this is that if we have a positive rational number, when we look at that, it's really important that dividing the constant 1 by a positive or negative infinity is still 0. And we'll talk about that. One of the things that students struggle with, that infinity plus infinity, we really can't do addition and subtraction with infinity, but infinity times infinity, we know will be positive infinity. And it's the weird concept that we can deal with the product of infinities, but we can't actually deal with the sum or difference or the addition or subtraction of those infinitesimals. Right, so we'll do a couple examples. It's definitely not a bad idea to maybe go back and take a look at your notes from chapter 2. We did infinite limits in that section, and I'll be using some of the techniques that we picked up in that. Now, this is right off of those kind of classic limits we looked at. We know that this is equal to 0. And if you think about graphically what 1 over x looks like, and I'll draw it out right here, it's got a vertical asymptote at x equals 0, and then a horizontal asymptote at y equals 0. Really importantly, that where we see this limit is here. that is the limit as x approaches infinity of 1 over x squared, and we can see that that's equal to 0 because the y value, or the output of that function, is getting closer and closer and closer to 0. Conceptually, it's important that there does not exist any real number that will make that equal to 0. But if we let this function kind of, travel on for infinity, eventually it'll be so close to 0 that we can call it 0 when we introduce that infinity concept. Okay, next one looks immediately more difficult for sure. It's taking the limit as x approaches infinity. The technique we talked about in our chapter 2 section was to multiply by 1 over the largest degree in the numerator. And the logic behind that is if I have, x in the denominator, a constant over x is the limit as x approaches infinity is 0. But if I have x over a constant, that's going to be positive infinity as well. But typically we want you to identify the highest degree in the numerator and then multiply the numerator and denominator by 1 over that highest degree. Now what that ends up doing to our limit is we now have the limit as x approaches infinity. I'll write them all out. We have 4x squared over x squared minus x over x squared plus 2 over x squared divided by 6x squared over x squared plus 5x over x squared plus 1 over x squared. That's a mouthful for sure, but as we start to simplify these, what this looks like is the limit as x approaches infinity of 4 minus 1 over x plus 2 over x squared, all divided by 6 plus 5 over x plus 1 over x squared. And the concept that we use here is the idea of the sum and difference rules and the kind of product rules of our limits, that because these are separated by terms, I can do each term individually. So the limit as x approaches infinity of 1 over x is 0, and 2 over x squared, and 5 over x, and 1 over x squared. So what this limit ends up being equal to is 4/6, which does reduce into 2/3. Now, what this means, and I'm not even going to try to draw the graph in the middle because I'm sure I would butcher it, but if we looked at this graph as we go to positive infinity, so right here, y is equal to 2/3, I would actually have to look to see if it's above or below, but we do know that the function is either approaching that from above or approaching that from below. We will talk more about, in this chapter, how to determine what that is. Probably the easiest way is to maybe put a gargantuan number in for x, like 1,000 or something like that, and see if the output of the function is larger than 2/3 or smaller than 2/3. And then we can tell in a simpler rational in this case. All right, I think I'm going to split the video here. Oh, well, let's do one more. It's pretty similar to what we just did. It wants us to take the limit as x approaches negative infinity. Now, you have to watch, and this is kind of similar to the concept we use, that if I'm approaching, not sure why that bracket's there, I'm just going to erase that at this point. If we approach negative infinity, then inside this bracket, I will have negative infinity minus 3, which is just negative infinity squared, times negative infinity times, now this is a tricky one, 1 minus negative infinity, that's a product. So if I talk about 1 minus negative infinity, this is the same thing as 1 plus infinity. We can multiply infinities, we can't add or subtract them. And so in my last bracket, I would have infinity again. Well, negative infinity squared is positive infinity times negative infinity times positive infinity. A positive times a negative is a negative, and then a negative times a positive is a negative. Now, what's very important about this is that this is not a number. And that means that the function as x goes to negative infinity, so the far left-hand side of our graph, we are not approaching a value. It's going down to negative infinity. And we're going to kind of combine those. And maybe I am going to finish, CND now here, because we can also look at the limit as we go to positive infinity. So it's the same, it's a similar question, I should say, that this actually is a little bit of a typo. It should say the limit as x approaches positive infinity. And if we approach positive infinity, what I would have is positive infinity squared times positive infinity times 1 minus infinity, which is negative infinity. Well, what we end up getting in that case is negative infinity. And what this graph looks like, and this is some of that math 30-1 creeping back into calc, is that we have x-intercepts at -2, +1, and at +3. We actually know that this graph has multiplicity 2 at +3 as well. But because of my left hand and right hand infinite limits, we know that my graph goes down to negative infinity as x goes to negative infinity. It has to, due to multiplicity, rise up through this point, change directions, and then really importantly, change directions on that last x-intercept. Now, everything in the middle there is going to be covered in more detail in chapter 5. Really what we're looking at today is that this right here shows me the limit as x approaches negative infinity, I'm just going to cop out and put f of x there, is equal to negative infinity. And this behavior shows me the limit as x approaches positive infinity of f of x is also equal to negative infinity. And that's why the graph opens downwards, which is something we introduced in a general way in Math 30-1. We are now looking at much more specific algebraic techniques for determining those things.